Okay, so for number one, where the dominant allele is the non-disease, and then the recessive allele is the disease, which is 1 in every 150,000. So in order to find just that one allele, you'll divide 1 over 150,000, and then take the square root of that, since you're just finding like the one allele according to the Hardy-Weinberg equation. And so you get 0.0026. And then in order to, again, referring back to the Hardy-Weinberg equation, you can just subtract this allele frequency from 1, and then you'll get 0.9974, and that's going to be your dominant allele. So then for C, it asks what is the frequency of the DD genotype in this population. And so that's going to be your p squared. And so you just take that allele that we found for D, and you square it, and you get 0.9948. And then it wants to know the heterozygous one for part D, and so that's going to be your 2 times PQ. So you do 2 times the dominant, or the recessive allele times the dominant allele, and you'll get 0.0051 for your frequency. For number 3, you...
Alright, so for question number 2, the first one, part A, says the term in the Hardy-Weinberg equation represents the frequency of the IB allele is, so up here we wrote all the different variations of the Hardy-Weinberg frequency, the equation that we have, and we're going to take a look at this one. And so we're looking for the IB allele, which is going to be right over here. It's going to be Q. So this is going to be the population of the IB allele. The term that represents the IA and the IB genotype is going to be right here, 2PQ, because this is a heterozygous genotype that we're looking for. The next one, B, says DiGeorge syndrome is an autosomal dominant disorder that affects 1 in 4,000 individuals in the human population. The 1 in 4,000 individuals in the population affected by this syndrome is represented by this term. So because this is an autosomal dominant, we're going to be looking at not only the p squared, but the 2pq as well, because both of these genotypes are going to display the phenotype for the DiGeorge syndrome. So that's the answer to these two. And then for C, it says this question refers to part B and the other 3,999 individuals, where is that represented in the equation? And we take a look, that's going to be the q squared, because that's what's left over after we've looked at these two. So this is going to be the amount of recessive, the people who don't have that syndrome. Moving on to part D, it talks about ducks, plumage, and the different phenotypes that we can see. There's 3 different phenotypes, so we're going to be using this equation down here. And it asks for which term represents the frequency of the MD allele. And so that's, okay, taking a look at that one again, at 4D, I was looking at the wrong one on my paper. 4D, we're looking for the recessive phenotype in here. And so this answer is going to be just R squared. This one right here. That shows the the homozygous recessive that we're looking for. Part E, this is the answer that we're looking for, the malted duck, right? So we're looking for the dominant allele, which is going to be this, anyone with a P in it. So it's going to be P squared, 2PQ, and 2PR. So all of those are going to show the frequency of that allele. In E, it says this question refers to, for F, the human disease that results because of SNP. And SNP is a change in the single nucleotide within a gene. And so in humans, we see that in sickle cell anemia. So that's the answer for F. For G, it says blank's a term that describes a trait that produces a single phenotype in 99% or more of the population, and that's monomorphic. Even though it's not completely 100%, we see at least as a rule 99% of the population has that phenotype. In H, it says blank is another name for a local population, and that's a deme. And then I, it talks about what genes in humans did we read from the reading that are highly polymorphic, and that's MHC. There's several hundred alleles in humans that code for that, but we each have 2. So that's an example of a polymorphic gene.
Okay. For number 3, it's the Marfan syndrome, which is autosomal dominant. And so for number A, it's asking for what the frequency is for the non-disease allele, which is going to be, we're just going to have that represent little m. And so for the dominant one, it's 1 in every 6,000. So you'll take the 5,999, divide it by 6,000, and take the square root of that to find the individual allele. That gives you 0.99992. You subtract that from 1 with the Hardy-Weinberg equation, and you'll get the Marfan allele frequency, which is 0.0008. Did I say no zeros? And then C, you're going to find, it wants to know for the heterozygous, so you do the 2pq, so 2 times the dominant and times the recessive allele that we found, and you get 0.00016. And then for D, it wants to know out of a population of 5 million people how many heterozygotes are expected. So you take that number and you multiply it by the heterozygote allele that we found here, and you'll end up getting 800 heterozygote individuals. So for number 4, it's talking about 3 different genotypes, and these are the observed genotypes that they found. So you have R2, 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 R3, and then R3 and R3. And so the total number was 190. So for number 8, it wants you to determine the allele frequencies for the R2 and R3 alleles. And so since we're just trying to find one, we have to take into account both of these for our equation. So you do 2 times the observed, which is 135, and then we also have to take into account this one right here. And so you'll do the 44 plus 380, which is the total amount doubled, since we're taking into account both of those, as well as this one. And so when you solve that out, you'll get R2 equals 0.826. So in order to find the frequency for R3, you can just subtract it from 1, and I got 0.174. And just to double check, I plugged it into like the same equation here, and I got 0.174. So then for part B, it wants you to use the chi-square test to determine if the population is in Hardy-Weinberg equilibrium. So first you want to, so if you're going to use this equation of P2 plus 2PQ plus Q squared, or sorry, P squared, equals 1. So I take the R2 allele that we found up here, and you square it, and then you multiply it by the total population, which was 190. And I get an expected value of 129.63. You do the same thing for the R3 allele, and you square that individual allele that we found, because this is like your Q squared. And then you have to do the heterozygote, which is the R2, R3, and so in the equation that would be the 2PQ. And you plug in those individual alleles, multiply it by the population, and these are the expected values you get. So for the chi-squared equation, it's going to be observed minus expected squared over expected. And so I plugged those in. This represents the R2, this represents the R2, R3, and this represents the R3. So once I did the math for those ones and added them together, you get a chi-squared value of 7.08. So for C, it wants you to interpret this. So since we have a large chi-squared value, it does not support the Hardy-Weinberg equation or equilibrium, and so it does deviate from that.
Go.
Alright, so for question 5, we're given this information here, the frequency of these different alleles, and they're in order of dominance, so this is the most dominant, and this is most recessive. And so to find all of the values for the Hardy-Weinberg equation, we can square each of these values to find those squared, and then do each of the combinations to find all the heterozygous possibilities. So you'll do 2 times the CCH and the CD to get that, and you just do that for all the different combinations you can make. And so for question A, we're looking for the frequency of C, CH, and CCH. And so we can come over here and find that value there. For CBC, we can come here and find that frequency here. And for the CC, we can come here and find that one there. And so for B, we're looking for a pale gray coat, which is the CB, and it needs to be heterozygous, and there's a population of 2,000. So the only heterozygous that makes a pale gray coat is this one here. And so you take that and multiply it by the population of 2,000, and you get 150. And for C, we're looking for a white coat with dark eyes, which is the CD. And it also needs to be heterozygous for a population of 5,000. And so there's two heterozygous combinations that can make that, which will be this one and this one. And so you add those together and then multiply it by the population, and you get 920. And then for part D, we're looking for CCH, CB, or CC in a population of 15,000. And so we can come over here and find the CCH, CB and add that to the frequency of the CC, and then you multiply it by the population and you get 3,113.